In this section, we're going to talk about rates of change. So dy dx gives the rate of change in y with respect to x. We can take some applications, and instead of using x and y, we can use other variables, but it's the same idea. The derivative is a rate of change. So let's look at an example. The cost in dollars of producing x items in a factory each day is given by c of x equals, and you have a cubic here, cubic polynomial. So the first two terms represent the cost of labor. The third term, 5x, is the cost of raw materials. And then you have your fixed cost at $2,200. So let's answer some questions. Find c prime of x, which is the marginal cost function. So the derivative in terms of this application is marginal cost. So c prime of x, we'll use the power rule because this is a polynomial. And we're going to get 0.00039 x to the second plus 0.004x plus 5. Easy enough. So that's our marginal cost function. Find the marginal cost when 150 items are produced and interpret what this means. So we need to find c prime of 150. And so grab a calculator. We'll punch that in, 0.00039 times 150 squared plus 0.004 times 150 plus 5. So we get 14.375. So if we round that, $14.38. Okay, so what does that represent? That represents the rate of change of cost right when you've made 150 items. So basically, what it's going to cost to make the 151st item. So it's an estimation for that. So I wonder what the actual cost is to make the 151st item. Well, let's figure out the cost of making 150, and we'll subtract that from the cost of making 151, and that will be the actual cost of making the 151st item. And let's see how that compares with that marginal cost that we calculated using the derivative. It should be close. So we're going to do c prime of 151, and save you some work, I already punched that in. It should wind up equaling $3,448.19. And then C of 150 is $3,433.75. And so the difference between those winds up being $14.44. Which is pretty close to that estimate we got using C prime. Let's look at another example. Water is draining from a swimming pool. The remaining volume of water after t minutes. So, you have to keep track of what we're dealing with. V represents volume of water, and it's in cubic meters, and our time is in minutes. All right, so there's our equation. Find the average rate at which the water leaves the pool in the first 5 minutes. So average rate of change, that's slope. So when you see average rate of change, think slope. And so we're thinking the first 5 minutes, that's from t equals 0 to t equal 5. So we're going to calculate the slope. So we're going to do v of 5 minus v of 0, so the difference of the y's over the difference of the x's. If we plug those numbers in, what are we going to get? We're going to get 200 times 50 minus 5, so 45 squared. And then minus v of 0, which will be 200 times 50 minus 0, or 50 squared, all over 5. Let's see, I could do some, grab the calculator, but that winds up equaling a negative, which makes sense, because it's water is leaving the pool, 19,000, and this would be cubic meters, because the volume was in cubic meters, and remember the time was in minutes, so cubic meters per minute. So that's the average rate of change. It's losing 19,000 gallons, 19,000, cubic meters per minute. Find the instantaneous rate at which water is leaving at 5 minutes. So at that specific instant, what's the rate at which water is leaving the pool? So the instantaneous rate refers to the derivative. So we're thinking v prime. So we want to calculate the derivative at 5. So let's first of all calculate what v prime is. And and sometimes we get sloppy and write just something prime. We should write dv dt to be a little more precise. And so if you look at let's move up here to the function, there it is. We're going to use the power rule. We're going to take this 2, we'll multiply it out in front. 2 times 200 is 400. And then times 50 minus t to the first power. And then times, don't forget the chain rule, now we have to do times the derivative of the inside function that was squared, and the derivative of 50 minus t is a negative 1. So we wind up getting negative 400 times 50 minus t. That's our derivative. So now let's calculate that at the 5-minute mark and see how fast water is leaving at that instantaneous rate. So we've got negative 400 times 50 minus 5, which is 45. And so that winds up being minus 18,000 cubic centimeters per minute. So the average rate of change was 19,000 cubic centimeters per minute over those first 5 minutes. But you can see that at the 5-minute mark, it's actually less than that average rate of change. So that's another example of using a function that represents some application and using derivatives to describe what's going on. Let's look at one last example. Find the rate of change in the area of this triangle as theta changes. The rate of change in area as theta changes. Rate of change is derivative. In the area, I'll use a capital A. I don't want to be confused with the A in the picture. Maybe I should just write area. So d area, d theta. That's what we're looking for. Okay, and then we want to do it at the instant when theta is equal to 60 degrees. So what we need to do is we need to come up with a function that represents the area, and then we'll find the derivative of that and evaluate the derivative when theta is 60. So looking at this picture, we have, it's not a right triangle, so we can't just say 1/2 base times height. We've got 2 sides and the included angle. And so you might remember that the area of the triangle is going to be 1/2 times the 2 sides times the sine of the angle between them. And so that's our formula for area. So we could even write this as a function. A of theta is going to be 60 sine of theta. So let's find the derivative. Let's find dA d theta, or A prime. And the derivative of sine is cosine. So we get 60 cosine. And now we're going to evaluate that when theta is 60 degrees. So let me write this as A prime 60, or pi over 3. Doesn't matter. So we're going to get 60 times the cosine of 60 degrees is 1/2. So that gives us 30. Now, what does that mean? What does the 30 represent? Well, if you go back here and look at what we're differentiating, and that's why I like to use this notation instead of just calling it A prime, the derivative of area. So area, what units will area of this triangle be in? It'll be in whatever the units are for the side squared. So centimeters squared, and then d theta. And when we're doing calculus, we take the derivative of sine was based on the fact that we were in radians. So it's going to be centimeters squared per radian. So 30. Oops. No, that's not the right color. How about here? 30 centimeters squared per radian. And so that's the rate of change in the area as theta changes. Okay, some problems from 14a, starting on page 347.